This is SpaceTime Series 25, Episode 129. Are we finally seeing the first light in the universe? The innermost structure of a quasar jet? And NASA's Perseverance Rover spots some intriguing Martian bedrock. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Just days after officially starting science operations, NASA's James Webb Space Telescope quickly propelled astronomers into the realm of early galaxies, previously hidden behind a veil of time and distance and well beyond the grasp of all other telescopes. And Webb is now uncovering what could be light from the very first stars in the universe. It's revealing a very rich tapestry where the first-forming galaxies look remarkably different from the mature galaxies we see around us today. The new observations, which are reported in the astrophysical journal Letters, suggest the onset of stellar birth may have begun as quickly as 100 million years after the Big Bang 13.82 billion years ago. If correct, it's an historically significant discovery. The universe's first stars, known as population 3 stars, were formed directly out of the primordial elements created in the Big Bang. Now that means they're almost exclusively composed of pure hydrogen and helium, together with only trace amounts of lithium and beryllium. That's because these were the elements made in the Big Bang. All the other elements in the universe, those which we know today, were manufactured by those first population 3 stars, either during their lives or when they died. And these elements, which astronomers refer to as metals, are incorporated into all subsequent generations of stars. Astronomers coarsely classify these stars as either metal-rich population 1 stars such as our Sun, or metal-poor population 2 stars such as those found in the Milky Way's galactic halo, and which may have been formed directly out of the ashes of the original population 3 stars. The importance of population 3 stars cannot be overstressed. They're responsible for bringing the nascent universe out of the cosmic dark ages. Before these first stars began to shine, there was no light in the universe. They brought in the epoch of reionization, when the intense ultraviolet radiation generated by these first stars began ionizing the primordial hydrogen and helium which filled the early cosmos, making the universe mostly transparent and appear the way it does today. Because of their unique composition, astronomers speculate that population 3 stars would have been extremely luminous, far hotter than the biggest spectral type O blue stars today. And they would have been huge, with masses between at least 60 and possibly over 300 times that of our Sun. But being so massive means they would have burnt through their nuclear fuel supplies really quickly, possibly in less than 1 million years or so. And that explains why there are no population 3 stars seen in the universe today. The hope of detecting a population 3 star has always been one of the prime objectives of the James Webb Space Telescope. And so the presence of potential population 3 stars could explain the discovery of 2 exceptionally bright galaxies by Webb, which existed just 300 and 400 million years after the Big Bang. These extremely bright galaxies have puzzled astronomers. The young galaxies are transforming gas into stars as fast as they can, and they appear to be compacted into spherical disk shapes that are much smaller than galaxies like our Milky Way. One of the study's authors, Tommaso Trieu from the University of California, Los Angeles, says pretty well everything astronomers are seeing through Webb is new. The telescope is showing an incredibly rich universe, far beyond what astronomers have imagined. And these early galaxies are very unusual in many ways. The 2 exceptionally bright galaxies existed apparently 450 and 350 million years after the Big Bang, and they represent some of the most distant starlight ever seen. The more distant galaxy, referred to as Glass C12, which is believed to date back to at least 350 million years after the Big Bang, eclipses the previous distance record holder, GNZ11, which existed some 400 million years after the Big Bang and was identified back in 2016 by Hubble and Keck observatories in deep sky programs. Based on earlier predictions, astronomers always figured they'd need to search a pretty large volume of space in order to find such ancient galaxies. So these new observations coming so quickly represent a whole new chapter in astronomy. Now, while the distances to these early sources still need to be confirmed with spectroscopy, their extreme brightness remains a real puzzle, and it's challenging science's understanding of galaxy formation. The thing is, the Webb observations are nudging astronomers towards a consensus that an unusual number of galaxies in the early universe were much brighter than expected, and this will make it easier for Webb to find even more galaxies in subsequent deep sky surveys. To be what they appear to be now, or at least now according to Webb, the galaxies would have had to start coming together maybe just 100 million years after the Big Bang, and that's much earlier than anyone ever thought. Nobody expected the cosmic dark ages before the first stars began to shine to have ended so quickly. It means the primal universe would have been just 1/100th of its current age. The study's authors are also amazed at being able to measure the shapes of these first galaxies. Their calm, orderly disks question science's understanding of how the first galaxies formed in the crowded, chaotic early universe. There are lots of galaxies seen by Hubble just a few 100 million years later, which look like train wrecks, and so these Webb images are a real contradiction. This remarkable discovery of compact disks at such an early time in the universe was only made possible because Webb's images are so much sharper in infrared light than anything Hubble could produce. Treyu says these ancient galaxies are very different from the Milky Way and other big galaxies we see around us today. As to why such early galaxies are filled with so much light, one possibility is that they could have been very massive, with lots of low-mass stars, like later galaxies. But it's the alternative possibility which is proving more intriguing. They could be much less massive, consisting of far fewer but extraordinarily big bright stars, namely population 3 stars. Indeed, the early observations suggest that the stellar populations in these galaxies are devoid of any heavy elements, and therefore they could contain at least some population 3 stars. This report from ESA TV.
For the first time in human history, we have the opportunity to directly observe the first stars and galaxies forming. Webb's infrared vision makes it a powerful time machine that will peer back over 13.5 billion years, pushing beyond the limits of Hubble's deep fields that showed us young galaxies when they were only a few 100 million years old and were small, compact and irregular. Webb's infrared sensitivity will not only look back further in time, but will also reveal dramatically more information about stars and galaxies in the early universe. While Hubble looked at toddler galaxies, Webb will see the baby phase. Webb's data will also answer the compelling questions of how black holes formed and grew early on, and what influence they had on the formation and evolution of the early universe. Today's universe is populated by galaxies, cosmic islands made of hundreds of billions of stars. Their sizes and shapes are vastly different, holding clues to how they formed and evolved. In the first few billion years, the universe was very dynamic, with galaxies undergoing merging events or being ripped apart, and were peppered by supernova explosions from short-lived massive stars. Operating at infrared wavelengths, Webb can observe the bulk of the light from these primordial galaxies and reveal their dust-shrouded starbirth and matter-absorbing black holes. Webb will also shed light on dark matter, the material that fills the cosmos but is not directly visible. In this way, Webb will complement ESA's Euclid mission that will map the geometry of the universe and is specifically designed to study dark energy, the force behind the universe's accelerating expansion and dark matter. Stars shrouded in clouds of dust, molecules in the atmospheres of other worlds, and light from the first stars and galaxies. With its suite of state-of-the-art instruments, Webb will push the frontiers of our knowledge of the solar system, of how stars and planets form, and of galaxy formation and evolution in new ways. Thanks to the rapidly evolving field of exoplanet studies, planets beyond our solar system, Webb will be able to contribute to key questions such as, Is Earth unique? Do other planetary systems like ours exist? Are we alone in the universe? Webb will study in detail the atmospheres of a wide diversity of exoplanets. It will search for atmospheres similar to Earth's and for the signatures of key substances such as methane, water, oxygen, carbon dioxide, and complex organic molecules, in the exciting hope of finding the building blocks of life. In this way, Webb will complement ESA's Atmospheric Remote Sensing Infrared Exoplanet Large Survey, ARIEL, a space telescope that will study what exoplanets are made of, how they formed, and how they evolve. Closer to home, Webb will also study the outer planets in our own solar system. Many exoplanets resemble Neptune and Uranus. Thus, studying planets in our own solar neighbourhood can provide new insights for better understanding planetary formation in general. Stars transform the universe's simple elements into heavier elements and, through supernova explosions, spread them throughout the cosmos. Observing in the infrared part of the spectrum, Webb will be capable of peering through the dusty envelopes around newborn stars. Its superb sensitivity will also allow astronomers to directly investigate faint protostellar cores, the earliest stages of star birth. Webb will study brown dwarfs, dim objects with masses in between those of a planet and a star that are not themselves massive enough to start thermonuclear reactions and become fully fledged stars. Webb will determine how and why clouds of dust and gas collapse into stars or become gas giant planets or brown dwarfs. Webb will also see the most massive stars explode as supernovae and leave behind more clouds of dust and gas, along with the precious heavy metals that enrich the cosmos to form new generations of stars.
This is SpaceTime. Still to come, the innermost structure of a quasar, and NASA's Perseverance Rover spots some intriguing Martian bedrock. All that and more still to come on SpaceTime. Astronomers using a global network of radio telescopes have observed the narrowing of a quasar jet for the first time. Quasars are powerful jets of matter and energy, bright enough to be seen across the other side of the universe. They're generated as material falls onto an accretion disk around a black hole. Material on the accretion disk bumps against other material there, causing an immense amount of friction and consequently heat. The powerful gravitational forces of the black hole further compound the problem by crushing and tearing matter apart at the subatomic level by immense tidal forces, releasing even more energy. Eventually, most of this material will pass beyond the inner edge of the accretion disk, a point of no return called the event horizon, beyond which it'll fall forever into the black hole singularity, a point of infinite density and zero volume where science's understanding of the laws of physics breaks down. However, a small amount of material on the accretion disk gets caught up in magnetic fields, which then fire it out as powerful jets perpendicular to the disk at close to the speed of light. It's thought most, if not all galaxies, host a supermassive black hole at their centres. And when these monsters feed on a passing star, planet or gas cloud, they generate an accretion disk, and that can produce a quasar. So these quasars are narrow, collimated jets of material. But exactly how and where quasar jets get collimated has been one of the long-standing mysteries of science. The authors of this study have moved a small way in answering that question by capturing an image of a quasar with the highest angular resolution ever obtained. The observations show the deepest part of the jet in a bright quasar known as 3C273. The authors found that the jet flowing from the quasar narrows down over a very long distance. And the narrowing of the jet continues for a long way, well beyond the area where the black hole's gravity dominates. and the results showed that the structure of jets in this quasar is similar to the jets seen being launched from nearby galaxies, ones which are far smaller. And all that suggests that the collimation of the jet is independent of the activity level of the host galaxy. The new findings, reported in the Astrophysical Journal, provide important clues to the unravelling of the inner workings of quasars. This is SpaceTime. Still to come. NASA's Perseverance Rover spots some intriguing Martian bedrock, another 5 spy satellites launched by Beijing, and later in the Science Report, warnings that the average lifespan of the humble honeybee has decreased by 50% since the 1970s. All that and more still to come on SpaceTime. NASA's car-sized 6-wheeled Mars Perseverance Rover is targeting a new sediment-rich bedrock outcrop at the base of Jezero Crater's river delta. The science team have named the area Yori Pass, and they've been eager to explore the region for several months after spotting the rock, which is similar to one Perseverance collected samples from back in July. The feature is so tantalizing for scientists because it's a sandstone, which is composed of fine grains that have been carried from elsewhere by water before finally settling down and, over the eons, forming stone. Perseverance's samples are central to the first step in NASA's European Space Agency Mars Sample Return Campaign, which began when the rover cached its first cored rock back in September 2021. Perseverance Deputy Project Scientist Katie Stack-Morgan from NASA's Jet Propulsion Laboratory in Pasadena, California, says mission managers often prioritize study of fine-grained sedimentary rocks like this one in a search for organics and potential biosignatures. What's especially interesting about the Yori Pass outcrop is that it's laterally equivalent to Hogwallow Flats, where Perseverance has already found fine-grained sedimentary rocks. That means that this rock bed is located at the same elevation as Hogwallow and has a large traceable footprint visible on the surface. The hunt in Jezero Crater for biosignatures, that's any characteristic, element, molecule, substance or feature that could serve as evidence of ancient life, is one of Perseverance's 4 primary scientific objectives. As well as 14 rock core samples, the rovers also collected 1 atmospheric sample and 3 witness tubes, all of which are stored in the rover's cache. After it's collected its sample from Yori Pass, Perseverance will travel some 227 metres to the southeast to a mega sand ripple. Located in the middle of a small dune field, the ripple, called Observation Mountain by the science team, will be where the rover collects its first samples of Martian regolith, that is, crushed surface rock and dust. Perseverance and its tiny 1.8 kilogram rotocopter Ingenuity landed in Jezero Crater back in February 2021 on a mission to search for signs of past microbial life on the red planet. Jezero Crater was chosen specifically because it formed an ancient lake bed and contains a vast river delta which delivered sediments from further upstream. And those sediments would have contained nutrients which any life on Mars, had it existed there, would have thrived on. And all that makes Jezero Crater a prime hunting ground for astrobiologists. China has launched another 5 spy satellites, bringing Beijing's total constellation of surveillance and reconnaissance spacecraft to more than 232. The latest launches include a Yogang 34 spacecraft aboard a Long March 4C rocket and 4 Gofeng 03D satellites aboard a Series 1 rocket. All 5 spy satellites were flown from the Jiuquan Satellite Launch Center in northwestern China. Beijing describes these spacecraft as being intended for commercial remote sensing services, for land resource investigation, for natural disaster monitoring, for urban planning, agricultural crop monitoring, and for public safety. However, military analysts all agree they're spy satellites, equipped with high-resolution optical and multispectral synthetic aperture radar imagery systems, or electronic signals intelligence gathering surveillance technology. It's all designed to provide continuous reconnaissance and monitoring of areas of interest to Beijing, part of what Chinese President Xi Jinping and his communist government describe as preparations for war. This is SpaceTime. that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.